Ladies and gentlemen, welcome back to another live stream. So this is part 2 of our series of creating a Vulkan engine by the assistance of AI. So let's continue pretty much. Okay, so please join my Discord server. You can find the link down in the description below. So you get notified of new streams pretty much. Well, yeah, okay, fine. All right. Let's pop out the chat. And let's go. All right, so I think we're good to go. All right, so starting off before I forget, I did one thing. I changed one thing from my previous stream's setup, which is I've gone to Visual Studio Installer, right, and then modify. And in desktop development C++, I added Clang tools for Windows. Now what that gives us is, if you go to your path, right, let me go to program files x86, and whoops, hold on a second, let me just do it this way. Well, all right, anyways. Okay, so if you go here and then you go to Microsoft Visual Studio 18, in my case, build tools, and VC and tools, and so you got like two tool chains now, one for LLVM, which is Clang, and MSVC. So we're gonna go with LLVM, x64, and lib. And as you can see, you got a few things here. You got Clang, okay, 22. Wait, not lib, sorry. Bin, I mean. And here you could find Clang compiler, as you can see, and even ClangD, which is required by ClangD here. Now, in the previous stream, we were just using ClangD, the extension installed in a temporary folder, which worked just fine. I mean, it's nothing wrong with that. But today, since I wanted to change the compiler to ClangCL anyways, instead of like LVM, basically instead of MSVC, I gone ahead and basically installed the ClangCL toolchain, as you can see from like the Visual Studio installer. And then I basically just took the ClangD, like just copy the path and go to settings here, open settings UI, look for ClangD path, and just copy your path right there, as you can see here, and it would work out just fine. Now it's going to use the official ClangD that is supported by Windows. And Nikita ED, welcome to the live stream. And quiet you survive coding. I mean, honestly, what I'm doing is not really considered like 100% vibe coding. I mean, I'm just kind of making the AI write crap for me. Like, I just want to move fast and break things. And honestly, I hate writing C++ nowadays. Yeah, just for entertainment. I mean, I always program for entertainment, really. I always program for entertainment. So if you're expecting anything else, I mean, who knows? Something could come out of it. You never know, but I'm always coding for entertainment. And it's not entertaining to write C++ and like Vulkan boilerplate code. Right? I like to explore. I like to try new things, research new technologies. And yeah, so right here, the AI allows me to, for example, in this stream, we're going to try some very like modern Vulkan extension that I've never tried before, and hopefully would help me do that easily. I see. I like problem solving, which LMs completely take away. But no, there's still problem solving. I mean, you still guide the AI step by step. Otherwise, it would just create crap code. And also another problem is, another thing though, is that the actual problem solving is not in writing the code. The actual problem solving is in debugging the code. That's why I got here the Vulkan validation layers, I got the Vulkan caps viewer, I got render doc, I got insight systems, I got insight graphics. So you kind of become more of a debugger and architect than a coder, right? So the AI does the coding part for you and like the research part for you. I mean, not like, I mean, just going ahead and like exploring the internet essentially, and like compiling the data that you need essentially. But anyway, let me show you what I'm talking about here in a second. So we got this cube that we basically have vibe coded, quote unquote, in the previous stream in 3 hours, only 3 hours, and it's very robust. We handled all edge cases, and I basically made sure that the code is very clean by going step by step with the AI, by making it, first of all, go ahead, make a window, then go ahead and make a clear screen with VKCMD, clear color, and so on. So, and obviously I'm also using version control. That's also required. So yeah, now let me show you one little thing that, so for example, let's go with Insight Graphics here since I have an NVIDIA GPU. And now look at what I could do here. I could start an activity, and then you basically put your application executable here, and then your working directory here, and then you go with the graphics capture, then you go with Vulkan, and you launch the graphics capture. Then you get this, you capture a frame, and then you get the frame saved in here, and then you could basically open that. Wait, how the heck do you, okay, there you go. So you just start, you can either start the graphics debugger, or you could click on replay capture, and essentially it would replay all the graphics API calls that you've made. Like as you can see here, and it would just run it, which is pretty cool. But anyways, let's go with the graphics debugger. Now, as you can see all sorts of things about your application here. So like, wait a second. Right. Let's do something like this. Okay, cool. So as you can see all the commands that is currently in this frame that is being ran for Vulkan, and you could see the delta T of the CPU, and you could even collect a GPU trace, etc. Also, for best performance for like NVIDIA, make sure to go to the NVIDIA control panel. And then basically go to manage. Wait, first of all, actually, I think you gotta go to, yeah, the desktop, and then you gotta make sure to enable desktop setting, developer settings, and then you're gonna get unlocked this guy right here. And then make sure to allow access to the GPU performance counters to all users, so you can get more details in Insight Graphics. But yeah. All right, do you use ASAN UBs? Honestly, I've never used them before, but we might try to set up them at some point, honestly. So thanks for reminding me. Anyways, so as you can see here, we got the frame, and here we got the synchronization points. And we got the graphics pipeline here, and then we also got draw call. And you can start a live replay. And boom, now you got all of this cool stuff. And you could even like zoom in and see exactly what's going on, and so on. You could see the history of the pixels over multiple kind of like frames and so on. And notice here in the objects browser, these objects are actually named in flight fence and so on, because we've used the debug utils extension, which is pretty cool. Otherwise we would have just had it like named just a generic name. But yeah. All right, so yeah, pretty sick stuff. And you could even go ahead to the graphics pipeline here, and I believe you could go to API inspector, and you could see your vertex attributes, as you can see here. Like it's called in position, in color, and the format, binding, offset, etc., etc. Like you could click the position, and there you go. This is the vertices in position. You could change that to in color, but that doesn't mean anything. Diffuse color, you could visualize the in position attribute as a color, and so on. Pretty cool stuff. You could even look into the memory here. Walaikum assalam, welcome to the live stream. Default cube as always. Okay, and here we're looking at the memory of this kind of vertex buffer and stuff, which is pretty sick. And we got this thing right here, which is just like primitive topology, etc., etc. And you could even open up the this guy right here, as you can see. So like all the data in the spreadsheet, and you could even save that spreadsheet. I don't remember how do you do that? Yeah, save as a binary, I think, maybe. I mean, that's just save as a binary. I'm pretty sure there was a way to, maybe not. I don't know. I don't recall. Or maybe you could, yeah, you could just copy CSV and then give it to the LLM to help you debug that, for example, which is pretty sick. Or you could even do something even cooler, which is export to JSON, or actually even better, export all pages to JSON. So it would like export all of this information, all the pipeline information to JSON, and then you would go to the desktop and you would save it, and then you would get a file like this one right here. As you can see, which is a JSON, and it would contain everything about your pipeline, and then you could feed it to the LLM. So if you have some issue or whatever, it would hopefully help you find what is the issue more easily. But yeah, or you could even like use RenderDoc Python API. But yeah, there's just a lot of ways. I just wanted to make sure that you guys know about this tool. It's pretty mind-blowing if you don't know about it. But yeah, stop live replay. You could collect the GPU timings. You could even collect a GPU trace. Hopefully it wouldn't mess with my live stream or anything. Yeah, seems fine. And there you go, look at that. So right here you could see all sorts of things about your performance counters in very much detail, pretty much. You could see how much PCI throughput there is, VRAM, L2 cache, and all sorts of cool things. But yeah. Anyways, and actually notice here that SPIR-V shaders aren't compiled in debug mode, so we can fix that. And you could even see the instructions, the SPIR-V instructions that's being used, etc. And yeah, there's just a lot of cool stuff here. There's even, I believe, like, where's the memory thing? Hold on. Let me try to find some buffer, maybe. Vertex buffer, for example, I think. Wait, device memory, for example, I guess. There you go, open in memory viewer. And there you go. Now you have even a memory map here, and you could see how VMA actually allocated the memory for you. So as you can see here, we have two heaps in my device. We have a device local heap, which is basically the dedicated VRAM. And then here we got heap 1, which is basically shared memory between my system, like shared RAM between my system and GPU, which is 12 gigabyte, and I have 6 gigabyte of dedicated VRAM. And here it tells you how much your game or application is using of VRAM, like in total, which is 37 megabytes currently, and 4 megabytes in the dedicated VRAM, and apparently 33.6 megabytes in the shared one. And notice here that VMA have actually created two device memories. One contains the vertex buffer and the index buffer, which is host, visible, and coherent, which exists in the shared RAM, right? And one in the VRAM, in the dedicated VRAM, which is device local, which only contains our depth image. As you can see, it's basically alone 4 megabytes. And notice here that this device memory have been allocated at like 4 megabytes, exactly the same way as the depth image. But on the other hand, this one though, it allocated like 34 megabytes although it's going to be using only these guys right here, which is not even 1 MB, right? Because, you know, it's preparing for more stuff to go into here. While here for the texture, it kind of chose to basically make a dedicated allocation. And here you could notice how much big is each one. So like this is the depth image memory. And this is the memory that the vertex buffer, index buffer, and other buffers would go into, for example, and so on. But yeah, it's pretty cool, lovely thing. There's just a lot going on here. It's amazing. Here you could see like the event details. You could see exact parameters that have gone into the pipeline and like the commands and so on. But yeah, that's just a little primer, I guess, on how to use the graphics debugger. There's also even like Insight Systems, which gives you more information about the CPU timing and all sorts of cool things. But yeah, that should be enough introduction, I guess, for now. Anyways, so what we're gonna be doing, let's see. So last time we wanted to create that, hey, my problem in 3D programming, how to make good transparent faces. Honestly, I've never tried that before. So once we get into it, we'll see how to fix that. Honestly, so yeah. But anyways, let's see what we got. So first of all, I'd like to change my compiler to Clang CL. Okay, let's see. Can you change my CMake presets compiler to Clang CL? All right. I was using MSVC. Last time I was using MSVC. Now I'm switching to Clang CL, which is basically Clang, but with MSVC ABI. So it should work just fine with the, and it even uses the NLD linker apparently, which is cool. Why I thought to do this? Well, basically because I was searching on the fast noise library, right? And I found this fast noise 2. Wait, fast noise 2, GitHub. Clang CL is great, although like you just said, doesn't fix the MSVC runtime. Actually, no, it does fix it. It's way faster and, you know, it just Clang pretty much. It's the Clang frontend. It just have the compatibility with MSVC, which is pretty nice. So you don't get issues with other Windows libraries and so on. But anyways, so here we got Fast Noise 2, which is like a SIMD noise generation library that is created in C++ 17. And it's very fast for like noise stuff, which we're gonna need later on. And let's see where the AI have got into at this point. What it's doing. Did it have some issues or what? Apparently couldn't find SDL3. That's interesting. I mean, if it is enabled to do that, then interesting. And boom, right now we're compiling using Clang CL LLD, which should be way faster, and it should also gives us way better errors, and should hopefully also allows us to use later on ASAN and UBSAN. I believe that's LLVM tools, but yeah. So that was the first step. Second step, I'd like to make sure that the shaders are getting compiled in debug mode. And hopefully we should be able to change into like slang instead of, there you go, cool. Slang instead of GLSL, because we're going to be doing some cool things today with the modern extensions like device address and so on, hopefully. I'll see. Done builds, links, and runs clean with. All right, cool. So git commit, or you know what? Clean up the generated shaders and make sure they're compiled in debug mode. When in debug. Yeah. When debug, yeah, pretty much, I think. Configuration, yeah. Other than that, let's just start there for now. So as you can see, added, I believe, -G. Where did it add that? Oh yeah, there you go. Cool. So basically on config debug, it added -G. Otherwise, it add nothing, which is cool. So it basically uses these kind of like, what they call, I forgot their name. But yeah, these are useful for like if you're using Ninja multi-config and so on. They work way better than if conditions. In fact, they wouldn't work on if conditions. But yeah. We're not using, I think, Ninja multi-config, but yeah, well. I don't know why it keeps on messing with the SDL3. Weird. Weird. Okay, the other nice thing about like an LLM is that it could use like spurv this to read the assembly itself, which is cool. Lovely. Now, let's make sure that it's still working fine. Okay, perfect. Perfect. All right. So here we're gonna git commit, or you know what? Can you? Yeah, just fine. Okay. Git commit and translate the shader, and use slang instead. Let's go. Look at that. What's up? Access files outside. Why would want that? Okay, I guess maybe it's kind of like doing a trying it out, maybe. And there you go. It rewrote the shader in slang. Because like GLSL like language becomes very ugly once we get into like buffer device address and all sorts of crazy things. Like the syntax becomes so ugly because the language wasn't designed, you know, with that in mind. So it was kind of just like glued in essentially. While slang, on the other hand, is a modern shader language, so we have like first class support for such advanced stuff. But yeah. It didn't change the CMake just yet. I wonder if it's just testing to make sure that it's that everything is like properly done. Ooh, wait. Oh, yeah, another cool thing about slang, I just realized what's going on here, is that it could use slang compiler itself, right? Instead of having to basically run the GLSL shader in my program, then figure out if it's good or not, it could just use the slang shader compiler directly and spurv this assembler to figure out if everything is sane first, without having to run the program, which is pretty cool. Look at that, it already fixed some few stuff. It just looked up the assembly and made sure that it fitted what it expected from the GLSL translation. For example, it was missing the column major, as you can see here, and it added it itself once it realized what's going on with the assembly there. Pretty cool. The other nice thing also about slang is the fact that you could have multiple like entry points in one shader, and you could have generics, and even have like a freaking standard library for all sorts of things, and like a module system in general, so you could have multiple files and like reuse functions and so on. But yeah, Python with brackets equals Python. What? Python with brackets. Yeah. I even have better reflection, I believe. And I have been thinking for a while now, should I stop it? Ah, there you go, it's writing. What the heck did it change again? I'm not sure what it's trying to do. Why did you move back to CPP from Zig? And welcome, Vortex. Well, I actually didn't just move from, you know, like Zig to CPP or back to C++. But I also changed from Rust, Java, Kotlin, JavaScript. Yeah, so I like to try a lot of languages, pretty much. And I ultimately have gone back to C++ for a lot of reasons. First of all, the industry standard for graphics programming is pretty much just C++. Like the libraries that you're going to find for graphics for Vulkan and so on is going to be written in C++ or at least C. But even in C, you're going to have problems. Like for example, VMA, which is like the standard memory allocator, it's in C++. And obviously you could indeed like use these from Rust and Zig through a binding or just like using the raw API. But you'll always have that. Wait, what's going on here? The verification shows memory computes. The result chain is identical. All right, cool, lovely. So as you can see here, it kind of iterated itself, made sure that the translation is sane through this dispervi disassembly, and then it's pretty smart, man. It's like for us humans, what we would have done, we'd have just like, you know, wrote the shader and just hoped it worked. Hoped it matched the same like GLSL kind of semantics, but here it didn't. It just freaking like compared the assembly. Now remove the old GLSL files. Oh my god, that's insane, bro. That's insane. But it's not working. Bro, all that work of checking stuff up, and it still didn't do it. Oh crap. Alright, let's see if it's gonna figure it out. I'm not sure what's the problem exactly, but let's see. Alright, so there's no validation errors. I mean, hold on, let me grab my Vulkan configurator. Do you want to download? No thanks, not now. Alright, so let's activate the validation layers and let's see if there's some validation. Okay. Wait, inside systems Vulkan was loaded with the inside. Oh crap. Alright, so there doesn't seem to be any warning here, which is interesting. Yeah, maintaining a wrapper is really hard as well, but Zig is awesome. Yeah, I really love Zig, don't get me wrong. I love Zig, I love Rust. But honestly, I think at this point, you're just better off, you know, choose your field, choose what you enjoy the most, and just see what the industry uses, which language the industry uses, and just stick with that, honestly, like for real. Like if you like Vulkan, for example, and graphics program in general, then it's C++, no doubt. Don't try JavaScript, don't try Rust, Java, Kotlin. You'll always find some walls, you know. And obviously, like if you really want to do it, you can do it, but still, you're always gonna find yourself. Do you know Python? Obviously, yeah. I know Python too. Do you have any particular questions about it? Yeah, I pretty much tried all sorts of languages. One language that I have been like hearing a lot nowadays, but I haven't tried it, which is like Odin, but so far I didn't hear any particular like very convincing argument to try. Like maybe if Odin was came before like Zig or Rust, maybe I would have been impressed. But since it came after, I just couldn't really like justify trying it kind of so far, but yeah. Anyways. All right, so let's see what's up going on here. Now the cube isn't being drawn anymore. Let's see if it's configured it out. It is not being drawn anymore after slang change. Let's see if we can figure it out. So it did this assembly apparently. But yeah, the ecosystem really like of the language is what really plays a huge role pretty much. It's not really about the language itself, but about the runtime and about the ecosystem. But yeah, it depends on your use case though. And especially like right now with vibe coding, like you need a stable language like C++. And honestly, C++ is a pain to write yourself. But like if you're gonna vibe code it, like make the AI write the syntax bullcrap, then it's great. And it's been thinking for so long, it just sucked at this apparently. But yeah, worst case scenario, you could just like, you know, revert this change and just forget about slang. But let's see, hopefully if you can figure it out, figure out what the problem is. I mean, from a hindsight, let's see if we can figure out the problem too. Let's go. Okay, hold on. It did something. It just spurvy disassembled again? What the hell? Weird. Is there like a slang extension by any chance? I have been learning OpenGL and Zig for like the past month. There were definitely some issues, but I got through them. Thinking of sticking with Zig even after I switched to Vulkan. Yeah, Zig is fine. Zig is fine as long as you can deal with like the LSP and the tooling problems and like the ecosystem problems and obviously also the language instability, then that's fine. But honestly, as a language, I really love Zig. I really, really love Zig. But yeah. All right, so what it's doing here. Anyways, let's go back into. All right, let's figure this out. Why it removed though that column and major thing? So what's going on? So what's the deal with Snake? It's like another shader language, or it's just a compiler to SPIR-V? Yeah, it just like all the shaders compile to SPIR-V. Like Vulkan can only accept SPIR-V. But why I wanted to switch to Slang, it's just because of a lot of reasons, especially that I want to go into like GPU driven development, and Slang is just more ergonomic for that. Like, for example, if you want to use the buffer device addresses and so on, let me do a quick comparison test. Compile. All right, lovely. Oh my God, it's gonna do it. Interesting. So there you go. It's gonna try to test the difference between the assembly between both, and then make sure it's doing it right. Hopefully, let's see if it's can figure that out. But yeah, as I said in GLSL, if you want to do like buffer device address, then you gotta do some weird syntax crap with buffer device address and so on, and with like buffer references, sorry. And there you go, like the GLSL way works. But the slang way, for whichever reason, it doesn't work. I mean, it did switch to like that column major thing, but then now let me look at the pipeline to check push constant size. Yeah, graphics is so fun. It can be very torturous. Like if you want to do actually something, like want to ship something, then graphics is not for you. But if you just want to thinker and you just want to try new things, new techniques, and just learn something, then yeah, graphics is so great. And like especially with AI now, you could just try things and just see what sticks. You could try all sorts of cool things. But yeah. All right, so that doesn't work for whichever reason. Yeah, I'm not very familiar with slang. I've never programmed in it, so I can't really tell what's the issue, unfortunately. GLSL uses OP matrix times matrix plus call major. Slang uses OP matrix times vector plus row major. Interesting. I mean, yeah, it had that like... I'm not sure why it removed it. I mean, it added it here somewhere, but it removed it afterwards. That's strange. Or maybe we should just not use slang at this point and just stick to GLSL. Bro, it's so slow. That's weird. It shouldn't be that hard. You know what? We also have Gemini. We could ask Gemini too. But I'm curious if it's gonna get it or no. It's gonna fix the issue by itself. Yeah, that sucks. That sucks. I think I'll scrap the idea of using slang and just continue with other stuff. Yeah, I feel like it's stuck in an infinite loop for whichever reason. No, they do not match exactly. Honestly, I don't have some big dreams with graphics. I picked it up as a hobby and I just want to build a basic render and build a game with it. Pretty much the same. I think pretty much all like graphics renders, at least probably most. You just start that way. But yeah. All right. So what's up? Interesting. Says plus. Bro, stop it. It's just stuck there. Let's see. Matrix multiplication order, major issue. Yeah, because this model, for whichever reason, I'm not sure if it got downgraded or whichever. But right now it's so stupid. It just got like stuck in a. You know what? Honestly, I feel like it's better maybe to just reset the whole context and just start a new session. Maybe that's why it's stupid. Because it was fine. Now, for whichever reason, it just sucks so slow. It's so dumb. And this is one big problem with AI is that it's not very reliable, especially if it's a free model like we have here. But yeah. And it would have been cool if there was like a way to basically control how much it can think, because it thinks too much. Yeah, it's so trash, dude. You waste your time on getting the perfect prompt while you could have done the work yourself. I mean, we're testing it. We're trying it. I mean, at any point I could just like, revert this whole commit and then just try again with some other thing or just do it myself as you said. But yeah, let's just see. Let's just see how far can it go. I mean, it was working fine. I don't know what's up now with this. And yeah, it just stuck. You know what? You know what I'm gonna do? I'm gonna revert the changes here, right? Let's go. Oh crap, wait. Wait. So replace GLSL with slang. Outgoing changes. Did it like commit this part or what? Yeah, it did. All right, let's just go back to this one. Check out, I think. Or do you like drop this or somehow or whichever? Yeah, let's just start a new session. Let's start a new session, okay? And read the code base. And let's see. So it would have fresh context and hopefully would be way better. So I just switched to slang. Look at the last commit. But now it's not rendering the cube anymore. Let's see what it's gonna say. It's probably just the column major thing, but let's just see what it's gonna say. Would it get stuck again or what? Let me look at the last commit to see what's changed. Yeah, so right now we got it. Yeah, probably just like a freaking context issue. Yeah, so I guess always start with a new session. Cause yeah, I was very surprised. Like, how the heck did it get so dumb so suddenly? All right, let's test right now. And boom. All right, so we're using slang now. Cool. So this was the issue. It was just the order of some operations that were changed, and yeah, that's that. Okay, so now we could hopefully move on to the next thing. Git commit and implement vertex pooling using device buffer address. Obviously, make sure to activate the extension. So basically, we're gonna move into like a data-oriented model kind of thing when it comes to GPU programming, and this is actually what like the modern APIs are really converging into. So instead of you giving the GPU like commands and these kind of abstract concepts like a descriptor set and the vertex buffer and index buffer and vertex state and all sorts of crap, no, you don't have that anymore. Eventually, what the modern APIs are converging into is that you treat everything as just memory. You just move this memory from here to here. That's all. There's no concept of descriptor sets or vertices or whatever. So here we're going to be, instead of like giving vertices as a vertex buffer, we could basically create a like a storage buffer or whatever, you know, write the vertex data into it, and then just give the shader. We would just give it like the address to that buffer, and then it would go itself and pull whatever data it wants from it, instead of us describing the vertex attributes in you know, in the actual code, which kind of suck, honestly. Brent, I think a little Timmy will join in a sec. Little Timmy, you mean Theo or Timmy? And it's thinking a lot, bro. What the hell? Come on. Let me just do this and do this, because that's too much. But yeah. Otherwise, other than that, we're also gonna use like virtual allocators for VMA. So instead of like having two buffers, one for the vertex buffer and one for the index buffer, and like one buffer for each chunk, in fact, two buffers for each chunk, you just have one huge buffer, which all the chunks is inside of. Little Timmy is used for word like a kid. Okay, I see. And it's just stuck. What the hell? Bruh. Really? You know, at this point, I think I'll just use Gemini and call it a day, for real. I'm not sure why it's so dumb today. Yikes. Yikes, yikes, yikes. I mean, let's give it some more time, I guess. Fine. Fine, fine, fine. So, actually, let's go to AI Studio, Google AI Studio. Let's go. And let's see if it's still in there. Yeah, it's still stuck. Well, that was unexpected. Let me just tell it something else. How about just git commit? All right, it did that very fast. What the hell? Bruh, really? Okay, how you'll implement vertex pulling using buffer device address. Okay, hopefully there you go. It didn't get stuck this time. I'm not sure what the hell was was that about. Anyways, here's how it implements in this code base. Enable the extension and features. Buffer address features. You could have just done it, I think, in Vulkan 1.3, but anyways, add address bit, cool, and push constants or UBO. Sick. Then update push constant, range size plus shader struct. Byte addressable buffer load. Okay, and raw buffer load. Sick. Pipeline remove vertex input state entirely. Remove. Okay. And let's see, hopefully it wouldn't get stuck this time. And yeah, thinking crap. All right. Yeah, I'm just gonna ditch this, honestly. I'm just gonna do it manually with Gemini at this point, because what the hell, bro? What the hell was that? No way. I'm not sure what's up. Anyway, fine. Hold on, let me just grab the chat in here, because okay. I'm gonna put the chat in front of me here, and so I could put the other window there. And let's go. All right, so I'm just gonna do this and this. All right, so let's just do it manually. Honestly, it's much better anyways, I guess, fine. All right, so everything good so far, right? Yes, pretty much. Let's sync the changes, fine. And all right, let's just move this out of the way. Now let's see what we're gonna do. So we're gonna go to the device features, or like Vulkan 1.3 features. There you go. And buffer device address. So it's a Vulkan 1.2 feature. So gonna add another struct here, Vulkan 1.2, and we're just gonna say buffer device address. There you go. Called vacate true. Whoops. Vulkan 1.2, and we're gonna do next is .p next here is equal to Vulkan 1.2 features, and let's go. Next, we're gonna update VMA and the buffer usage. So in init VMA, so we're gonna go right now to init VMA. VMA allocator, create info. Oh yeah, we gotta make sure to go into the flags, as you can see here. And yeah, the AI here kind of sucks. So let me just wait. How do you disable this? There you go. All right, so cool. Now create info flags is equal to device address bit. Wait, no. Well, I guess I just gotta, yeah, fine. So VMA allocator create buffer device address bit, just like that. Actually, wait, hold on, like this. Right, and next we're gonna go to the create vertex buffer. What the hell happened there? Let's go, and what we're gonna do next is retrieve the 64-bit GPU address. All right. And we basically just do it using this. Let's see, and obviously we're gonna add, I guess, a vertex buffer address to the struct, to the state struct. So here we're just using vacate get buffer device address. We're gonna get the device and the address info, which is just the vertex buffer that we created. And yeah, now let me just make sure to create that app state. There you go. So let's go to app state here, and let's just add this guy. Like this. Okay. T4BD is Vulkan object driven like OpenGL? Does it have VAO, EBO, VBO, or do you need to allocate everything yourself and map it? So there's kind of levels to Vulkan essentially. There is like Vulkan 1.0 where like a lot of Vulkan objects are, well, API abstractions that doesn't really align with the underlying hardware. But if you use modern Vulkan extensions like I'm doing here, like using buffer device address, using the new descriptor heap buffer, or using descriptor indexing, or like all sorts of cool stuff like this, then mostly the GPU stuff, like the Vulkan, you kind of like just have memory stuff, you know, like you just basically copy this memory from here to there, and it just works. You don't have that much like arbitrary abstractions between you and the GPU, essentially. So hopefully that answers your question. But yeah, all right, let's go to the next thing. So for the push constants here, what we're going to do is we're going to add this vertex buffer device address, just like that. And next, update the graphics pipeline. Manually in the shade, we tell the Vulkan that the vertex is empty. Oh yeah, cool. So now let's go to the pipeline state or vertex input. And we basically just remove all this binding stuff, I think. Yeah. So all that binding stuff gone. No need for attribute descriptions, binding descriptions anymore. And update the render loop. So you no longer need to call, you only need to bind the index buffer to drive and update the push constant. You no longer need vk cmd bind. Okay, vertex buffer. So we could, I guess, just remove this part. And the shader GLSL. So I'm gonna tell it that I'm using slang here. Very cool. And do you have recommendations for modern Vulkan resources? Yeah, definitely. I really recommend the new Vulkan 2026 tutorial. I think it's called How to Vulkan, or let me try to find it here really quickly. I don't know why the connection is slow. Oh crap, wait. Damn. Alright, it's back, I think now. Alright, cool. I don't know what happened there. Anyways, so I really recommend this one, this tutorial. It's very new, and I think it's by Sasha Willems. I'm not entirely sure, but I think it's by Sasha Willems. It's an updated tutorial, and it's using very modern patterns, like using Vulk, VMA, like we're doing, using GLM and SDL, instead of the old tutorial, which kind of suck. But yeah. All right, so cool. Now let's just go back into business and let's see. In Slang, implementing vertex polling with buffer device is very clean because Slang supports C++ style pointers and reinterpret cast. Now you just add uint64t here. Wait, it just added the vertex struct, or isn't it? Whoops, I think so. Wait, so we gotta add this to the push constants first of all. And then what it's doing next. So you got like the frag color is instead of in color. Okay, so yeah, wait. Does it cover everything? I need to start with yes. I really recommend this tutorial. It's pretty good. Pretty good, like the best in 2026. This would get you set pretty much. All right, let's see. I haven't followed it myself because, like, you know, I started very earlier than that. I actually started with where the tutorials were recommending some, like the Vulkan 1.0 way of doing things, which really sucked. But nowadays, modern Vulkan, it's a bit way better actually. But yeah. All right, so what we're doing here, so structure vertex, pause color. All right, so I've never used like slang before, so I'm kind of starting to figure out what the hell is going on here. And let's see. Let's see. So uint vertex ID. All right, so uint vertex ID is v vertex ID vert main. So basically we don't have, oh yeah, we don't have vertex attributes anymore because we're going to be using vertex polling. So essentially you can just remove this part, I think. Right. And then what? Then out float 3, frag color, color 0. And I guess apparently you probably don't need the location thing anymore. And finally, instead of in color here, you can just do this. Wait. So vertex vertices reinterpret cast. In the find identifier, reinterpret cast. Huh. Vertex v vertices vertex ID. PC vertex buffer address. And then v dot color here. And let's go. Next, you got the other things. Honestly, I'll just copy them. I'm really excited to learn Vulkan, but I want to spend more time with OpenGL first. And I apologize, the questions are too in or something. No, I'm basically making this live stream so you can ask questions. And yeah, it's good. Just stick with OpenGL, honestly. Don't really waste your time on that. I mean, like definitely Vulkan have way better debugging tooling, but it comes with a heavy cost pretty much. So I really, really recommend sticking with the OpenGL then for now. But yeah, all right, let's go to the next thing here. We could just like copy that over and we're good to go. Now here what we got, so float 3 frag color, color 0. And I guess we don't need that. And return float 4, frag color 1.0, okay. And then enable the buffer address feature. Yeah, does slang actually have a reinterpret address? Let's see. I mean, they do have reinterpret, not reinterpret cast. Yeah, let me ask it if it's sure about that part. But anyway, let's continue the conversion here and we can come back to that. So you must enable the buffer address feature. I've already done so, okay. And updates to allow BDA. And add the shader device. Oh yeah, am I doing that? Hold on, I probably have forgot about that part actually. Let's see. Usage, right? Yes, usage. So where we're actually using this create buffer thing. In fact, you know what? I could just do it here really. Fine. Let's just say vk buffer usage shader device address bit. Let's go. And get the pointer. Okay, we have already done that part, I think. Haven't we? Wait a second. Oh, I only did it, I think, here. But yeah, that's fine, I think. Yeah, no. Hold on. Go back. Not here. Here. In create vertex buffer, what we're basically doing is this. Wait, what? Bruh. Let's just copy this part and let's put it here. All right, now the disable, I did that. Oh yeah, we gotta definitely make sure that's the case. So let's go to the push constants. And let's make sure to set the address. So state push constants dot vertex buffer address. State vertex buffer address. Are you sure Slang have reinterpret cast? Usage is the frequency and type of allocations like the OpenGL static draw, etc. Or is it something else? It's more complicated than that. I mean, usage is honestly mostly just a hint flag in Vulkan for how you will use the buffer. And honestly, it doesn't even matter for modern GPUs. Like you could just like in Vulkan, you could just mix all of them together and like create all your buffers that way, and just pack your vertices, your indices, your uniforms, everything in one buffer. And it wouldn't really make a difference. In fact, I'm probably going to do that myself also. But on OpenGL, on the other hand, a lot of things are being done for you by the driver, so it makes way more difference. So like when you say static, then the driver basically assumes that that buffer would be static, and it would basically optimize accordingly. If you say dynamic, then it would make sure to use a staging buffer in the background for you in the driver, which in Vulkan I have to do myself, essentially. You see what I mean? So in some sense, when you're programming Vulkan, you're kind of like programming the OpenGL driver yourself, right? But in OpenGL, you kind of just have to guess what you're gonna do. And yeah, but if he got it wrong, then it basically kind of like resets and it just redoes everything over, which basically results in that frame hitch that sometimes happen in OpenGL games. But yeah, but like for simple games or like simple applications where you just use the API regularly, like the driver is pretty well optimized, the OpenGL driver, and like a lot of people that creates their own Vulkan driver ends up like creating something worse in performance actually, because they don't know what they're doing. But yeah. All right, so let's see what's going on here. All right, so what I asked, are you sure? Okay, yes, I'm sure. The return language, right? All right, let's try this out. Let's see if it works. And boom, expected an expression of type got bool. It confidently tells me, yes, it does exist. Bruh. Okay, let's try. So should I do this then? Well. Right. All right. Okay, so the vertex polling is actually working with slang. Sick. Very sick. Very cool. Though I do feel like it's a bit janky for whichever reason. I'm not sure why. Or maybe just because the shader is in debug mode or something. But yeah, that's cool. That's lovely. That's pretty lovely. So this is my first time actually programming in Slang, which is nice. But anyways, all right, so what we're gonna do next now. So that was vertex polling. So we just basically changed the, wait, hold on. Can I like just unify this somehow? Wait, how do you do that? Yeah, how do you unify this crap? There you go. Okay, cool. Lovely. Slang, it gives Rust and C vibes at the same time. Yes, it's pretty much a little bit Rust. I've never programmed in like Slang before. This is my first time. I was just kind of forced, like the agent that I was relying on to write the code for me just kind of flanked on me today for whichever reason. It was just stuck thinking and thinking and thinking, so I just did it myself with Gemini. But I mean, we could try it again, see if the agent right now works. I don't know. But yeah, either way, let's see what changes we have done. We basically converted into a struct here instead of like using buffer attributes, as you can see. Like, yeah, vertex attributes, we just make a struct. And then here we just grab the vertex ID of that particular vertex, like basically the vertex index. And in the push constants, we just store the address to the vertex buffer, right? So the pointer to the vertex buffer. And then here in Slang, instead of like getting this vertex buffer attributes, we just go straight up, grab the actual buffer address, and then we dereference, or actually not dereference it, but like essentially cast it into vertex pointer like you would do in C, and then you get back like a vertex pointer essentially, and then you could basically index into that pointer using the vertex ID, and then you could pull the vertex right from there. So now you don't need like the vertex buffer attributes anymore, and you don't need to bind any vertex buffer anymore either, which is our first step towards GPU driven rendering essentially, because we don't have to bind buffers anymore, at least vertex buffers for now. But yeah. All right, so what's going on here? Okay, we could just remove this one. It's not really required, as you can see. And yeah, that's it for the Slang shader. What's else? And finally, here's what we changed in the actual C++ code, apparently. These are just formatting stuff. So we just added the buffer device address feature. You cast it from opaque pointer to vertex pointer. Never knew you can do this much with shaders. Yeah, pretty much. Now this is that thing that like casting and all that crap. It's so ugly. It's so freaking ugly in GLSL. Let me show you how it looks like in GLSL. How it looks like in GLSL. Let me show you. That's why I've switched to Slang in this stream. And in fact, this is the first time I've ever programmed in Slang. So I'm just going with the waves here. And look at that. So this is what you're going to need to do in GLSL to get this to work. You got to first of all, like activate all these freaking extensions. That's the first thing. So the first one is buffer reference to use the buffer device address extension. And you gotta activate this one called shader explicit arithmetic type int64 to handle the uint64t. And then you gotta activate also GL ext scalar block layout to match the C++ struct alignment, no padding on vec3. Right? And then you basically kind of do this weird buffer reference crap to grab or like declare a vertex pointer, and then you can add, finally you can right now actually use it. And yeah, after that it's a smooth sailing kinda, right? But yeah, you see all these aerobics that you have to do. Yeah, but in Slang, it's very cool. Like, I didn't knew actually before today that you could do it in Slang this easily. So in Slang, since it's a modern shading language, you just do it like you would do in C++. You just freaking declare the goddamn struct. You put a uint64t in the push constant struct, and then you just like freaking cast that into the vertex array, because this is kind of like just a void pointer essentially to some degree, right? It doesn't know the type, so you just cast it to the right type, which is the shader that knows the actual type, which is our struct here. And yeah, and you just pull the freaking thing using the vertex ID. And here, obviously, you could use whatever other index you want. So you could basically index into the whole freaking vertex buffer instead of being limited to only one vertex. But yeah, it's pretty cool actually. Yeah, Slang for a random person will feel like a normal programming language, which is awesome. Yeah, pretty much. So anyways, so what we're gonna move on to the next thing now. So this was we basically implemented what this is called. Right. Well, it's pretty much vertex buffer address, let's say, or vertex polling. Right, and let's commit. Now, let me see if the agent right now works, because otherwise we'll have to code everything else ourselves, which is honestly kind of fine, but we're much slower that way. But let's hope that it would work now. Read main. Let's see. I really implemented it and it works. Bro, what? Okay, let's see. Oh crap, at least it actually found a bug in my code already. Not a bug, but a typo. Okay, let's see. What is it called? Vulkan 1.2 features. Yeah, so this is just a little typo that I made while typing this. Screw it. Run 20 parallel agents to make a real engine type of I hope, but this is just a free model, so yeah. All right, so that's that. And I guess I'm just gonna amend this commit. Oh, there's actually a validation error, huh? Wild. Okay, hold on. There's a validation error. I mean, it's actually quite interesting. So, was declared but one of the following? Validation errors. Okay, so basically, in like OpenGL, in Vulkan, you have this program called Vulkan Configurator. You just run it, and you just activate it. And once you activate it, now when you run any Vulkan program, it would tell you if you're misusing the Vulkan API. It's kind of like GL debug, like if you're coming from OpenGL. So in modern OpenGL, there is something called GL debug message callback. So this one, you gotta actually like set it up yourself. And in fact, even in Vulkan, if you want to like set up the validation layers, you gotta set it up yourself programmatically. But instead of doing that, you could also just use the Vulkan configurator and just activate it and make sure you're using the validation layer, and it just works, right? And you have all sorts of cool stuff here. That's crazy. You have an LDB in Vulkan. What do you mean? But anyway, so Wiki physical device features. I mean, let me see if it can actually like fix these issues itself. Run it and fix the issues. Let's see. Because last time I tried this thing, it just blocked for whichever reason. Let's hope right now we would go through it. Bro, what? Yeah, it's super slow, honestly. Really sucks, man. Bro, what the hell it's doing here? I mean, I kind of see the sentiment, but it should work without it. I'm not sure why. I mean, fine, whichever, as long as it works. There you go, cool, lovely. Now it's working. The configurator feels like LDB pretty much, which is cool in OpenGL, I guess, most of the time, and try random. Yeah, in OpenGL, the debugging experience kind of sucks, really. But like in Vulkan, this is what I really love about it, and sometimes even try to recommend it to beginners. It's because of these tools, debugging tools. OpenGL sucks at debugging tools. But Vulkan, on the other hand, pretty good. But like Vulkan gets in your way a lot when you're just trying to get by and understand how the hell does even graphics work. And that's why nowadays I kind of started to be honest with you, if I had to like suggest some way for beginners to really like understand how graphics works, honestly, I would just tell them to use WebGPU in JavaScript, vanilla JavaScript, WebGPU, not WebGL, WebGPU. That's pretty much honestly the best. If you just want to focus on the rendering while still using modern, uh, API kind of. It's pretty good, actually, because you don't have to worry about creating the context yourself and all sorts of crap. And like vanilla, I mean, there's still some ceremony there, but still, it's much more minimal. But yeah. Build succeeded, just filled order warning. All right, so what it was doing exactly? Okay, let me see. So 3 validation errors to fix needed for physical storage struct with flow 3. Okay, needed 4. All right, sick, lovely, cool. Tried WebGPU before. This was like a year ago, but back then I didn't know a lot of stuff about programming in general, so a bad start, I guess. Which language you use for WebGPU? Because if you have used like Rust or C++ or whichever for WebGPU, it really sucks, man. I don't recommend it. It kind of sucks, honestly. At that point, just use Vulkan. But yeah. But like, WebGPU in JavaScript, on the other hand, it's pretty cool. Is the base Vulkan 1.0 feature not in the 1.2 struct I need to use? Okay, cool. All right, so there was just some features missing, that's all. Nothing fancy. Right. So right now I think it got fixed. I think. Yeah, it got fixed now. Pretty much. All right, cool. So can we amend this? I think I tried that with TS or GS. I don't remember, to be honest, but it was very hard because of the lack of resource, unlike OpenGL. Yeah, that's true. That's true. The lack of resources really sucks. Yeah. But right now, I think nowadays it's a bit better, especially, you have AI. Although, honestly, AI is kind of a hit and miss. That's what really sucks about AI is reliability. Sometimes it works greatly, like it would surprise you at how good it is, and sometimes it would surprise you at how stupid it is. So like that's the problem with AI, it's inconsistency. So like when you're talking with, let's say, a human being, like with a person, like you can tell if they know what they're talking about or if they don't know what they're talking about, and then you could just go with that, right? But the AI, on the other hand, you can't really make that assumption. It's like every response would be very different. It's like you're talking to a very different person, kind of thing, you know. But anyways, so commit amend. I think vertex point, yes, commit. And let's sync the changes. Sick. All right, so what we should try to do next is okay. So all those issues really kind of made me even forget what I was trying to do. Let's see. Yeah, so next up, I think we could try, let's say, the uniform buffer address. Could you migrate the uniform, sorry, the frame data to, or you know what? Maybe we should try to, or yeah, fine, never mind. Yeah, AI as an instructor is cool too. I always ask you about OpenGL things to explain how it works on a low-level way. But as you said, sometimes it hallucinates. Yeah. Could you migrate the frame data to a buffer with buffer device address? Hopefully it wouldn't get stuck this time, because oh my god. Let's give it another chance. If it doesn't work, then I'll just do it myself. Alright, finally. Seems to be doing some progress now. So basically right now, instead of like holding the actual data itself in the push constants, which takes a lot of bytes, and like the push constant size is very limited, like 128 bytes until like 256 bytes. So instead of storing the data in line, you could just like use the push constants only for storing the addresses to buffers, essentially. And this is what we're going to do here. As you can see, it removed all those and only stored the address to the buffer and added a new struct called frame data. Big data. Okay, so main.cpp is we got frame buffer. Frame buffer? Oh, I thought it was like OpenGL frame buffer. All right, let's go. Frame buffer memory, vacant null handle, frame buffer device address, frame data map, cool. Next, what it did, it created the frame buffer. Cool. Nice, nice, nice. Ooh. Yeah, I got a validation error there. You see what's nice about this? In like OpenGL, here the validation error, you know, like the LLM could read the validation error and like fix it itself, as you can see here. So you see, and boom, it did it. All right, cool, lovely. All right, let's go next step. So basically created the buffer, the frame data buffer, and then there you go, and there you go. Wait, no, never mind. And here it just made sure to, it removed that stuff and it did it here. and then it just took that frame data mapped and it wrote to it. Now remove the unused vertex index buffer binds from record frame. No, we're still using the bind index buffer though, right? And yeah, cool, lovely. And yeah, that's it. So clean run, no validation errors. Here's what's done. Persistent mapped buffer, updated frame. What's a frame buffer anyway? A frame buffer. A frame buffer is basically something that you could render to. So you could make a frame buffer, let's say on the window, right? And then you render to that. Or you could create a frame buffer that, you know, you render to it like offline essentially. So it's not in the window. And then you could later on blitz that frame buffer into the window frame buffer, and then you're gonna see it. Like for example, let's say you're making a drawing app, right? Or like a render target also. Though a frame buffer actually means more than that though. Like a frame buffer could also be like the depth buffer too. So like honestly, the frame buffer definition is a bit ambiguous to be honest with you, but I would say probably a frame buffer is anything that kind of matches the like that you could render to essentially, honestly. Yeah, I mean, if I run here right inside graphics, for example, let me see. Yeah, I'm kind of struggling to actually explain this. But let's see, graphics debugger. Like for beginners, I really recommend using debuggers, whether it's RenderDoc or whichever. They're pretty useful. Like for example, here we got the graphics pipeline. So here we got like two frame buffers, right? We got the color frame buffer and we got the depth frame buffer. So here the color frame buffer just stores the rendered colors that we have. And here the depth buffer just stores the depth stuff. You've seen it before in Linux. I can open up an app in the terminal, but doesn't open unless you open your DE, which then renders. I think that's what you mean. I'm not sure. Can open an app in the terminal, doesn't open unless you open your DE, which then renders. I think that's what you mean. Yeah, honestly, I don't know how to explain it exactly, to be honest with you. It's just something that you kind of get to know at some point. But yeah. Anyways, let's move on to the next thing at this point. NVIDIA Inside Graphics, all right, fine, I don't care. Okay, so what we're gonna move on to next? It's time to just, all right, cool. So, okay, what we're gonna work on next? I think we could work on indirect drawing too. So we could move on everything to buffers, hopefully. All right, let's see the VKCMD draw. All right, let's try to tell it to make everything like, hold on. Can you implement indirect draw? Indirect draw, okay. Let's just see what it's gonna do, honestly. And let's see what it's gonna do. It's like opening an app that doesn't render in its window unless a condition happens, but the pixel that it wants to render are already present at a buffer. Like, I mean, I would explain to you not what a frame buffer is, because honestly, it's an abstract object that is kind of flawed, but I would describe to you what is a render target. So for example, let's say you want to make a drawing app, right? So a drawing app, you need to keep on rendering the same lines. So like you need to persist with the user drawn into the screen. So here you got like two options. You either store all the lines and all the modifications that the user have done, if it's a vector program. But if it's like, let's say, a raster program, then you just gotta store like all the pixels yourself in a frame buffer, right? Or you could use a render target, for example, like out of the screen render target. So what you do is you render you first of all create an off-screen render target, and then you render all the drawing of the user into that off-screen render target. And then what you do is every frame, you don't clear that render target. You just keep on rendering that render target into the window every frame. Yeah, it's very hard to explain just by explaining. I don't know. But yeah. Anyway, so clean run, no validation errors, no crashes, indirect draw is working. Clean run, no validation errors, no crashes, indirect draw is working. Okay, let's see what the hell it's done here. Add indirect buffer fields to app state. Okay, cool. Indirect buffer memory, sick. And then what it did is create indirect buffer. So here it created this guy. So basically here, instead of calling the draw command ourselves, right now we're moving all the draw commands into a buffer too. So what I'm trying to achieve here is that everything becomes in buffers. So we have like a data-oriented design, right? So everything becomes just data and memory. So we could unify and simplify the architecture way more. But yeah, so here we got index count and indices.size, first index, vertex size, create buffer, so indirect buffer bit, usage shader device address bit. And then here create the indirect buffer, and then you replace the vk-cmd draw indexed with draw indexed indirect. And then you give it that buffer, indirect buffer, and you're good to go. And boom. Now, all right, so okay, what we're gonna do next? Wait, hold on. Can you make all buffers contain all what is it called? All usage flags, because it doesn't matter on modern GPUs. So we can simplify our API into just creating GPU buffers instead of separate calls for vertex, index, storage, etc. Make sure to commit the current changes first. You start a draw command in a buffer as well. Yeah, exactly. So I'm trying right now to move the architecture of the engine, all of it, into buffers, right? So everything, even the draw commands, into memory. So when you want to draw stuff, instead of like going ahead and calling an API call into Vulkan and telling it to draw, what you do is that you could either do that in the compute shader, or you could do it from your CPU and you could just write memory. You just write bytes, nothing special, right? So basically what I'm trying to do here is that the thing is, these older APIs, these legacy APIs like OpenGL and even Vulkan without extensions and all sorts of stuff like that, what they're trying to do, they're just giving you these abstractions that are abstract. They have nothing to do with the hardware. The hardware doesn't know like vertex buffers or like index buffers or storage buffers. It just knows bytes. Okay, so here's some memory. I want to use this memory. That's it. It just knows that. But these like legacy APIs, because of a lot of trouble, they add all these abstractions in because of portability issues and so on. But now, like modern Vulkan versions with modern extensions, they're moving toward basically treating everything equally, just as memory, just like they're supposed to be. Nothing special, you know, and that's what I'm trying to move my engine to here, essentially. I want to treat everything as data. So I could simplify way more, essentially. And this is like the first time that I'm trying this, honestly, so don't expect much. All right, so KGPU. But how would you tell the GPU what the bytes you move to a buffer represents what command? Okay, hold on, let me just see what it did here. Right. And it works. Sick. Crazy. I wonder if there's no like validation errors. Yeah, there's no validation errors. Lovely. All right, let me see first of all what it did. What changes it did? Okay, so as you can see, it basically made use of all the buffer usages instead of me having to give each usage alone. And it even, yeah, it even made like a GPU buffer, nice, struct, which contains the buffer and the allocation and the address. Yeah, I would even go as long as not storing an allocation here, but yeah, either way, whatever. Next up, what's going on? So here we got the push constant, and notice here, the push constant, instead of having matrices and all sorts of crap, right now it only contains, we only use it to store addresses to other buffers. So here, it stores an address to the vertex buffer and an address to the frame data. How possible? Store color and face instead of vertex attributes. Whoa, G Gear, and welcome to the live stream. What do you mean? Okay, so here now we got like a vertex buffer, an index buffer, a frame buffer, and an indirect buffer. So this is the buffer that will still store our commands, our draw commands. And here we remove this stuff, okay. Next, now replace all the buffer creation functions with a single create GPU buffer. Okay, let's see. So you got the K buffer usage. Okay, so as you can see, our API is way simpler now. We no longer need to tell it what is the usage. It just use all usages, essentially. And next, what we got? If data equal null PTR, then VMA allocation create map to bit. All right, VMA create buffer. All right, data not equal null PTR, then VMA map memory and mem copy. Okay, I see what it's doing there. All right, and result the address. Notice how much code we removed there. Create indirect buffer. Yeah, we had, as you can see, we had all these kind of weird stuff for each buffer. Specialize it. Now we have one single function for all the buffers. Now simplify init Vulkan. As you can see, vertex buffer is just a GPU buffer that takes an allocator, a device, and the data, and the label for debugging purposes. That's it. No usage flags, no bull crap like that. Next up here, as you can see here, the command, the draw commands too, is just a GPU buffer, nothing special, right? So you just got like one indirect command currently, and you create a GPU buffer, and you just upload that command into memory, and that's it. Okay, so push constants, and obviously you make sure to put the addresses into the push constants here. All right. Update the record frame for the new struct. Make a CMD bind buffer. Okay, cool. And next, main CPP. All right, that's lovely. That's lovely. Isn't it better? And yeah. So this is GPU buffer unification. And I guess also indirect draw, right? We added indirect draw, I think. Did we? Yeah, I think so. Or we could just make the AI generate a message really quickly here. Yes, it's strictly better. GPU buffer bundles the buffer allocation address map pointer, no more scattered fields. KGPU buffer usage with all flags, never think about usage again, and modern GPUs don't care. Single create GPU buffer functions became one, and it is just 4 lines. Address auto queried, no manual vkk buffer address calls everywhere. Cleaner init cleanup, uniform pattern for all buffers. Want to commit. Refactor, introduce GPU buffer struct, and update buffer management in Vulkan. Sync the changes, boom. Already committed. All right, what are we gonna do next? All right, so what I'm gonna do next also, currently what we have is we have 2 buffers, one for the index buffer and one for the vertex buffer, which is not great. I mean, it's fine actually, it's really fine, but we could do better. We could go with VMA documentation really quickly here. And we could go to the virtual allocator. There you go. And I'm gonna make the AI read this. I'm gonna make it read the documentation of that. I mean, I know what it is, but you gotta learn what it is. I mean, it probably already know, but gotta make sure that it knows very well. Yes, that's the next step up from what we have now. Instead of n separate end objects, you would one large pool buffer, single big allocation with all usage flags. VMA virtual block matters within that buffer using VMA's call algorithm. Each gets an offset, handled but share the same. All the shader addresses are just address plus region offsets on modern GPUs. No wasted per line, read GPU. How do you plan on implementing it? So essentially, instead of having like 2 buffers, one for the vertex buffer and one for the index buffer, you'll just have one single Vulkan buffer, which contains all of them, right? And that virtual allocator in VMA could help you do that easily. So then your mesh doesn't become like Vulkan buffer. It just becomes like, just data. It's just index and size. That's it. So that's cool. Here's my plan. Data structures. GPU pool, single big buffer, VMA allocation, virtual block, manage sub-allocations, persistent map of whole buffer, base device address, GPU region, handle 4D, VMA virtual free, offset within the pool. Cool, clean up each region. Okay, try to implement it. Let me see if it would work. I've never actually tried this before. Like one time I tried it, obviously, but I did it manually. Like I basically used an offset allocator, a handwritten offset allocator, where I basically just packed all the data into one single buffer manually by myself. But then I realized that VMA already got that covered using a virtual allocator. So yeah. As you can see now, instead of having like 4 GPU buffers, you just have one single buffer, and then you got these sub allocations, which is pretty insane. Sub free. And let's see if it's gonna work. And it seems to be working just fine. So yeah, I think right now we probably only have like one buffer for everything. Clean run, no errors. That's insane. I mean, let me just make sure that's the case actually. Currently it's 64 kilobyte maximum. But yeah, virtual block. Uh, okay. Now let's see. Now draw multiple geometries. Let's see. Obviously, you gotta commit though. Let's see what it's gonna do next. Oh, session compaction. Okay. Oh, it's using instancing now. All right. Cool. You see how easy it was like adding instancing? It didn't have to add any vertex buffer attributes or whatever the hell. You know, you just create a new buffer and you store its address into the shader, push constants, and you just use it from the shader. That's it. Done. Boom. It's really that simple. No need for reflection and no need for attributes. No need for any of that crap. It just is. But the real question, oh, there you go. All right, it works. Lovely. Lovely, lovely, lovely. Okay, make the camera able to move around using WASD and the mouse. Obviously, lock the mouse at the beginning and toggle with ESC. So we're already at like 1,276 lines of code. That's crazy. Ooh boy. We might need though to do staging buffer for efficient updates. But yeah. I could make it like so it uses my camera to grab a texture and display it into the cubes. But I mean, the scriptures kind of suck, but honestly, we kind of gotta go through them anyways to some degree. I mean, I could make it use actually push the scriptures for that part, maybe. Yeah, we'll have to figure that out. Let me see if the camera works now. It works, but there's a few issues though. First of all, it's inverted in both axes, I think. Yeah, that's first. And second thing, it doesn't go towards my local direction thing, you know. The mouse, the rotation are inverted in both axes. Also, my camera should go in the local front vector global. There you go. And that works now. Lovely. Now generate a lot, like generate a lot of cubes to stress test it. Cam. Now we will increase the pool size to fit 10k plus cubes. And it would probably make a grid, I think, already. 4 megabyte, let's go. Crazy. See, make build. And let's see. Let's see. Oh crap, look at that, man. How much cubes is that, by the way? Wait. It's 10,000 cubes. So the camera should be a bit faster though. And my GPU is going insane right now. Though I could make it go in the like release mode. Wait, how do you do release mode? Hold on. Release mode. Oh, well, you just do this. You make preset. And then you go Windows release. And hopefully there's no issues with the release mode. I should test it more frequently. My God. And boom. And yeah, that's way smoother. And look at that, 10,000 cubes. Now I wonder how much in FPS this is. Okay, we could use just NVIDIA Insight for that. So NVIDIA graphics, build, window release, copy path, and you could just start an activity. And instead of debug, you could just go with release. And you're good to go. Graphics capture, launch, allow. Oh, but it's FIFO though. Yeah, it's FIFO. Hold on. So let me just switch it from FIFO to mailbox. So I could remove VSync. So I could see how much frames we're pushing in. And let's make sure to build this. And let's try again. Weird. I don't know why it keeps on crashing. Weirdo. Alright. Why it keeps on crashing? Let's see. Video graphics again. There you go. So I'm getting around 500 FPS with 10,000 cubes. 800, 900, 1000. No, that's frame count. FPS seems like 75. Weird. I mean, like... And also there's a validation error, by the way. Sync hazard. Ooh, crap. Wait a second. Yeah, let's just go back, honestly, fine, whichever. Let's just go with window debug for now. And let's tell it that. Oh, it actually only appeared in the insights. Or is it also in graphics? Hold on, in release. Let me try release mode really quickly. Yeah, it's just an insight problem apparently. Okay, you know what I'm gonna do actually? Can you calculate FPS and log it each second after aggregating it? What models are you using? Is that open? Yeah, Terraboom, welcome to livestream. It's Big Pickle, the free model of open code. Let's see how much FPS we're pushing. 1000. Cool. Though, if we're even seeing here, and we're not rendering anything, but still the FPS is still capped to 1000. But like 10,000, that's 1000 FPS. Crap. Crazy. It's 1000 FPS. Can you crank up the number even more? I mean, I think it's using instancing probably. So, yeah. It's using instancing. Now 32 megabytes. Okay. Well, I guess here we go, nothing. So let's go to release mode. And oh, actually, wait. I have the validation layers on and I'm still getting that FPS, bro. I'm getting 70 FPS now. With how much? 250,000 cubes. But wait, let's disable the validation layer because it adds some overhead. And yeah, it actually didn't really even matter, interestingly. And yeah, I'm getting like 72 FPS here, which is pretty sick. Awesome. Crazy. But yeah. All right. So that's pretty cool. Now git commit and plan out how you'll implement compute frustum calling. Load the instant thread ID model, transform unique cube-bounded sphere. Test against 6 frustum planes. I mean, go ahead. Yeah, it's gonna need index count, fine. Righty. Well. So basically the stuff that the camera doesn't see that is not inside of the frustum of the camera, and essentially what is the frustum of the camera is just this. So it's basically, as you can see, there's like 6 planes. This is the first plane, second plane, third plane, and fourth plane. So you just kind of like each instance, each cube or geometry or whichever, you check if it's inside of this frustum by basically checking it against the normals of all of these 4 planes, or shall I say 6 planes, because like there's even this and that, and you check if it's inside. If it is inside, then render it. Don't call it, like don't make it invisible. But if it is inside, then draw it. But yeah, but let's see if it's going to be able to do it, because it's such a big change. And I just told it to do it and just see what it would do. That would be interesting to see if it will figure it out. And it wrote the call slang shader. Weird, but okay. Right. Key bounding radius for group size, custom size. Would it remove instancing? Because I don't think instancing supports frustum calling, doesn't it? Or was it even using instancing though? I'm not sure. Actually, it wasn't using instancing, which is interesting, I think. But anyways, I mean, it's such a huge change. I don't think it would one-shot it. I mean, if it does, oh my god, that would be cool. And I guess it's done. All right, let's see if it's still working. And boom, initialization failed. Why? Let's see why. Let's activate the validation layer. Bruh. Check the logs, there's validation errors. Okay, and I can't see anything. Here's some other validation errors you have. Main CPP. Okay, so it's gonna query the alignment and it's gonna store it. Then it's gonna use it in the suballocate function, I think. Yeah, cool. Yeah, the validation layers are very freaking useful. But it's still not working, so and this time we gave it no validation errors, which is interesting. No validation errors, but I can't see anything. I guess it's time for some debugging, maybe. Okay, let's just try it. So But yeah, as you can see, nothing is visible. So let me check out inside graphics. Let me try to debug this frame and see what's going on exactly. Start activity. I'm not sure if I'm using debug or release. But let's just use release mode. Sorry, debug mode. Oh, I think I know why the hell this crashes. Because I think maybe because I have the validation layer on. Probably. Let me just restart this. Let's try again. Vulkan. Yeah, that's the case. Now let's try to capture F11. Whoops. And boom. Is it taking some time to open up? Oh, never mind. So you gotta start the graphics debugger here. And let's see what the hell is going on here. Oh crap. Well, how the hell do I even do this? I mean, you know what I could do, honestly? I could just export all these pages into my desktop. Wait, just delete this one. Hold on. Just do this, save. And can I do the same with this one? I wonder. Yeah, I guess so. Save as CSV. And let's see if we can give it to it. Wait, where's my, hold on, what the hell? Graphics pipeline. Do this. And this. Okay, cool. Now I'm just gonna make a little folder, debug or whichever call it. I'm just gonna put these guys here. And I'm just gonna take this, come here. I don't see anything visible. You can check debug data from insights in this folder. I'm not sure if that would help, but I never tried it before, so I guess it's perfect timing to try it out. And it's huge. It's a CSV. Oh yeah, crazy, it's a CSV. Oh crap, it would probably like block out the context. Yeah, maybe I should have not done that. Yeah, I should have not done that, man. That sucks. Yeah, I didn't think it was gonna... Like, what the hell? Anyways. Well, that's interesting. I'm not sure if I should stop it now. I'm just gonna tell I don't see anything visible, and let's see what it's gonna say. I kind of over-engineered that part. Yeah, I don't understand how to debug with the new setup though. The indirect draw. Though maybe I could be able to... Would I? How about render doc actually? True. I don't think render doc would help here either. Let's see. Okay, so I already found the issue. Interesting. Yeah, like render doc is completely broken. Yeah, I gotta find a way to debug the application with the current setup we have. We'll see about that later on, I guess. Wait, what? Okay, let's go to projects, move the build folder. And let's try to run it again. And yeah, I'm still not seeing anything, which is interesting. Yeah, we'll probably just revert this. We kind of got too far with that. Yeah, we definitely got too far with that part. Let me give it one last chance. After that, if it doesn't get it, I'm just gonna revert this feature for now and focus on something else. All right, instance, thread ID, the model center, multiply the model by 0001. What? Weird. Inside, we look through all the planes, all the Fresnel planes. We do a dot product with the center, plus the plane.w. Okay, but why the center is multiplied by a zeroth vector, except for the w, which is discarded anyways, too. Interesting. And if inside, then the index call buffer interlocked add index. Destination value, original value. So like base is equal to h plus idx times 20. I mean, let me ask you about this part actually. And RW byte address buffer. Or you know what we could also do? We could also use Gemini. Let's go. So new chat. Let's give it that and that. Why nothing is visible? After I added the compute call mesh. Bro, 1 minute of thinking, like. Yeah, we kind of overstepped there, honestly. We've gone too far really quickly, so no. Just... Yeah, let's just discard all 3 files. And let's see what we got here. So, where's my changes? How do you copy the other? Wait, no. Copy the commit hash. Drop commits until camera controls. That was working. Now reverted back to a working program, hopefully. Use Visual Studio like vars bat file. It keeps on forgetting that crap, which really sucks. It should really make like a freaking bad script here, but anyways. Alright. Crazy. Alright, so call Let's see if it's going to be able to call the meshes on the CPU instead of the GPU, because it kind of failed miserably with the compute shader. I mean, honestly, it's such a huge change. Like, you gotta figure out the pipeline and figure out all synchronization, all sorts of crazy things. And yeah, let's see. And no, that doesn't work either, which is interesting. Yeah, no. Let's just discard the file, and honestly, let's just change the topic. Let's just change the topics. Okay. Cube, or what is it called? Counter. I mean, let's just go up there and let's remove a bit. I don't know what's going on there. Let's see. Okay, way better. All right, let's just change the subjects for now, I guess. Fine. Read the code base. What abstractions you suggest? Can you abstract the the Vulkan shell boilerplate out of there? How do you plan to do it? Okay, let's see how it would look like. It takes quite a long time. Wait, main is still that huge? I mean, 700 lines is still big. I'm not sure what's going on there. Oh, because like that just removes the initialization stuff, apparently.